Welcome to our Chapter 11 problem solving video. Today we're going to cover one of every type of problem that you'll see in this type of chapter. We're going to start with the easiest type of problem. That's the conversion problem. We've technically already seen this problem in Chapter 2, but we've never really used pressure units. Today we're going to introduce our pressure units a lot more than we've ever done before. So PSI is the most common pressure unit in the United States. Millimeter mercury is the most common laboratory, or at least in a chemistry laboratory, measurement for pressure. ATM is the reference point for most people because there's 1 atmosphere of pressure on the world. So we're going to use these conversion factors, with ATM being our conversion point or our center point of the conversion. We have a table from chapter 11, I think it's table 11.1, that gives us all these conversions. These conversions will be given to you on the exam. So we want to go from PSI to ATM, making sure that our conversion has PSI in the bottom, so it'll cancel out with PSI. And then our next conversion has ATM in the bottom, so it'll cancel out with ATM and give us millimeters of mercury. Again, the table that I'm going to give you, table 11.1, is going to reference everything in regards to ATM, or average air pressure at sea level, which is 1 atmosphere. So you can expect to see this table on your exam. You can use these conversions for these type of problems. Like I said, we want to make sure that all of our units cross out as we're doing our dimensional analysis, and then we just get the proper units and our correct answer plugging into our calculator. So here's just a couple more problems. We could do this with a whole bunch of different units. Kilopascals is the more physics-based unit. Pascal is the fundamental unit. That's 1 Newton over 1 square meter. That's just a fundamental derivation of what force can be, or what pressure can be. Pressure is force applied over an area. So we're going to go into the simple and combined gas laws. These are very much so just plug and chug equations. So we have P1, V1, P2, and V2. I can give you 3 of any of these variables and leave out one of the variables. You're going to have to solve for them. Now, there could be some unit conversions in here if I ask for things in a specific way, but I'm not trying to trip you guys up. These are very simple problems. The ones that are a little bit more involved are the ideal gas law problems and using those type of equations with chemical reactions. We'll do a couple problems like that, one that's very similar to the challenge question. But for right now, these are very simple plug and chug equations. All you have to do is remember what the equation is. I'm going to be giving you the equation like I showed in the lecture, so no worries there. We know that pressure and volume vary indirectly, so they have this type of relation or this type of equation. We can simply plug in or rearrange for the variable that's missing, and then plug in our values, solve for the answer with our calculator. Pretty simple. We want to make sure all of our units cancel out and that the correct unit is the only resulting unit. If we have liters ATM, that can't be equal to just the volume. That's the volume times the pressure. So in this case, the pressure is going to cancel out with ATMs. So Boyle's law is our first of the simple gas laws. You can look at a variety of problems with these, but essentially, you have some starting volume, some starting pressure, some other volume or pressure. You need to solve for the next thing. So Charles' law is the next one. Charles' law relates temperature and volume. So as temperature increases, so too does volume. So this has a slightly different relationship. Before we had a indirect relationship, now we have a direct relationship. And so direct relationships are in this fractional type of notation. So V1 over T1 equals V2 over T2. It would also be okay to say T1 over V1 equals T2 over V2, just reciprocating or taking the inverse of this equation. If you were solving for T, you might want to do that. If you're solving for V, you would want to use it in the format that it is currently. So we can just make sure that everything's in Kelvin. For these simple laws, you don't have to make sure that they're in Kelvin. For the ideal gas law, which is the most important one, you do have to have it in Kelvin. So it's a good idea just to keep yourself honest and just always turn things into Kelvin. I mentioned this when we were doing Q equals MC delta T. You can get away sometimes with using Celsius, but it's better just to convert to Kelvin because when you're doing something important, you might forget, and then it's going to really come to bite you. So we solve for whatever conversions we need to, plug those values in, rearrange for the missing value, plug into our calculator and solve. So here are some more practice problems. Again, we're going to go through these simple and combined gas laws pretty quickly. You can pause as you like and kind of work through the problems on your own, but these are, I'm starting to sound like a broken record, plug and chug type problems. I can give you 3 or 5 variables. You'll see in the combined gas laws that we'll have 6 total variables. And the simple gas laws, we just have 4 variables. I can give you 1 missing variable. You can only solve for that missing variable. If I give you 2 missing variables, you need to ask me a question because I screwed up in writing the problem. You can't solve for 2 missing variables. So you just rearrange for the missing variable, plug in, hope your calculator did it right. Make sure that you plugged it in right to your calculator. So combined gas law, we're now going to have 3 different values. We have volume, pressure, and temperature. We talked about how these each relate to each other individually, but now we're going to show how they relate to each other as a group. Essentially, all the relationships between the 3 stay the same. So we could take these initial values, rearrange them for the ideal gas law. Pressure and volume are indirectly related. Volume and temperature and pressure and temperature are directly related. So we have this type of equation. If you don't quite remember, what direct and indirect relationships are, it's not going to be the most important thing, but it can be helpful with, real quick intuitive logic checks. Rearrange for P2, since that's the missing variable, plug in everything else. Make sure you convert to Kelvin if you want to be careful. You could get away with it in this case. The reason you could get away with it in this case is Kelvin is canceling out. Kelvin here cancels out with Kelvin here, so it wouldn't matter if it was Celsius and Celsius, Fahrenheit and Fahrenheit. However, with the ideal gas law, we're not going to have 2 temperatures. We're only going to have 1 temperature, and so there'll be no temperature to cancel out. So, more examples of the combined gas law. Avogadro's law relates volume and moles. Kind of everything that's related to moles gets named after Avogadro since he came up with the idea of the mole. Again, he's not a chemist, he's a physicist, but we could rearrange for N. Volume and moles is directly proportional, so we're going to have a similar equation as we did for volume and temperature. So 1 over the other. We could reciprocate this if we were solving for moles. That's what I would do in this case since we're missing our N2. But what they do is they, multiply and divide. Not a big deal. So here's some more practice with Avogadro's law. We're not going to... You might see 1 or 2 simple or combined, not and, simple or combined gas law questions on the exam. I'm mostly going to focus on the ideal gas law because that's the one that really matters. And how we get the ideal gas law is by combining all of the simple and combined gas laws. So the ideal gas law is PV equals nRT. In this case, we're missing V. You'll always be given R. Now, in the book, they might give you R, ask you for R, or ask you for things in slightly different units than I will. I will always ask you for R. I will always give you your R in terms of liters ATM per mole per Kelvin. That means that all of your units have to match that. So in this case, we're going to rearrange for volume. Pretty simple. All we need to do is divide by pressure. We'll get moles times the ideal gas law, ideal gas constant times the temperature divided by pressure. I apologize for these little boxes. I guess my software didn't download correctly today. So, pretty simple. Still plug and chug when we're given everything. One step further is turning these into reaction type questions like I do for the challenge question. So, more practice, we have volume, we have moles, we have temperature, we're missing pressure. We can rearrange for everything, take the PV equals nRT, divide by volume, and just solve for pressure. Pretty simple. ideal gas law and, gases in general are pretty conceptually easy. We had a couple, kinetic molecular theory concepts that we have to apply. But for the most part, chapter 11 is a pretty simple, just plug and chug type chapter. Now, moving on to problems that require a little bit more thought and care. We have a problem here asking us to figure out what the molar mass of a compound is. Now, they gave us the mass of the compound and most of our values for the ideal gas law. The only thing they left out was moles. So we need to determine the moles using the ideal gas law. Then the molar mass is just the grams per moles. So what we calculated for. So we have an extra variable here that we're not going to use until the very end. So we have all these variables. You should realize that the only equation you have that has all of these variables is the ideal gas law, PV equals nRT. We don't have N, so you need to rearrange for N. Molar mass is mass over moles, just like we said. And we need to take the mass that's given to us, divided by the moles that we solve for. Even though we don't have necessarily a mole of compound, we will be able to normalize this because the amount of moles always relates to the amount of mass. So, just more rules, double checking. We are doing the ideal gas law. Temperature is not canceling out with anything other than the ideal gas constant. I will always give you the ideal gas constant in terms of Kelvin, so make sure you convert into Kelvin. Here would be the mathematics for this after we've converted everything. Plug and chug, just like every other problem so far. The only thing that's different here is that we solved for moles, and now we have an additional step where we solved for moles, we were given mass, we need to divide these two quantities to get the molar mass, the actual ask of the question. So you could do this for a variety of problems. Here's another, setup for it. Here are some other practice problems in the back of the book. I'm not sure if these are part of the homework, but if they are, you can expect to see a bit of problems like these. The other type of problem that you can see from this, or more complicated problem from the ideal gas law, is what we will be doing for the challenge question. Now, we're going to be doing this for, a combustion reaction, not the decomposition of potassium chlorate, but same ideas apply. We're given some mass of the starting material. We're going to figure out how much of that product decomposes into these two species. However, we're concerned with the amount of oxygen. So we're given the partial pressure of oxygen. Potassium chloride's a solid. It doesn't have any pressure. Or the partial pressure of potassium chloride is essentially zero, so we can ignore it. In this case, we're just going to calculate with regards to oxygen. Now, here we have some rules just to follow to kind of get the correct answer. We've kind of talked through a lot of this, but, converting from grams to moles, we use our molar mass. From moles to moles, we use our mole ratio. Then we can use PV equals nRT to calculate for the pressure associated with the oxygen given off. We don't want to calculate the total number of moles of everything in the reaction, just of the thing producing the pressure, or just of the thing that we have the pressure of. So we'll be able to calculate for volume. I think I said calculate for pressure. We were given the pressure of oxygen, so we'll calculate for the volume of oxygen. So using these values, we can plug in. And at the end of the day, we'll figure out that this decomposition reaction yields 90.7 liters. So quite a large volume of gas, very small room worth, but still a good amount. Make sure that everything makes sense. If you have a large pressure, you should expect a smaller volume. If you have a smaller pressure, you should expect a large volume. You can always use STP kind of as a logical check. STP is, standard temperature and pressure. Standard temperature is 0 degrees Celsius. Pressure is 1 atm. And so that takes up about 22.4 liters. If we have more moles than that, we should expect more volume. If we have more pressure than that, we should expect a lower volume. Things like this can be used to kind of do these rational checks. So another example of this would be the decomposition of silver oxide into silver metal and oxygen gas. We're going to have the same thing as the previous problem. So if you have any questions on these type of problems, please feel free to reach out, as these are very similar to the challenge question that I'll review in lab this upcoming week. Hope you guys have a good week, and otherwise I'll talk to you later.